Here's a clean image of a vehicle, and that is how your training data looks like. Now, here's what we actually get in production. You can get motion blur, you can get glare, low light, you can get rain. Now watch what happens. When you get these degraded images, your OCR is going to fail and you're going to get poor embeddings. So naturally you would think, let's enhance the image, but here's a catch. We don't care to enhance the image just so that the image looks good. We care to enhance the image in a way that makes downstream systems that are going to use those images perform better. So you want things like, whether your downstream system is OCR or creating embeddings, you want them to be optimal. Not only that, there are many ways to enhance the image. So how do you know which operator to use? Are you going to deblur? Are you going to sharpen? Are you going to upscale the resolution? What if you need multiple enhancements and the order of those enhancements give you different results? So problems like these, they need reinforcement learning, and this is what we're going to talk about. So in this video, we're going to break down how this project uses reinforcement learning in computer vision, and we're going to cover the problem, the decision process, the reward design, the architecture, and the training strategy, and how to debug it so you can apply these ideas yourself. So why not just train a model to enhance the images? So that's what most people try first, right? Why not train a model using supervision learning? But here's the fundamental problem. There is no ground truth for the images. There's no correct enhanced image. So the only signal we can have is any of your downstream system improving. In this project, in this example, we're using a OCR system that reads the characters of the license plate, the alphanumerical characters. You can also have an encoder that generates a fixed size embedding that you can do other things with. So that's another downstream system. And so those signals come from a pipeline that looks like this. You get the image, you enhance it, you see the results of one of your downstream systems, and just in this example, you have an OCR, and you get a score. So here's the issue. The gradients do not back propagate through the downstream system and to the enhancement back to the image, because your downstream system are frozen. They're not part of the training loop. So you cannot back propagate through the OCR, for example. So you're stuck. You can measure the success, but you cannot directly optimize for it. And so that's where the problem becomes interesting. And that's another reason why we need the reinforcement learning. So whenever you want to optimize the system through a non-differential block, which is like an environment in RL world, then you can use reinforcement learning. Another reason to use reinforcement learning is actually that the action space is combinatorial. So let's say you have 10 operators, 10 enhancement operators to choose, and each operator has a few continuous parameters, like how strong do you want to apply it, or to which scale do you want to apply it, or to which region do you want to apply it. These are continuous parameters that are applied for each of the operators. So as you combine those things, the combinatorial space explodes. It becomes really huge. So reinforcement learning, it allows you to search this space efficiently by learning a policy that directly optimizes against downstream reward. Another reason is delayed credit assignment. So downstream model, they need to finish processing before we get the results. So the reward is delayed. So the only framework that can actually handle all of these problems we spoke about is reinforcement learning. So instead of predicting a single output, let's just say it actually generates a new enhanced image. All right. Instead of that, we're going to turn this into a decision problem. So the agent doesn't output an image, it's going to output a sequence of decisions. At each step, it's going to look at the current image, it's going to apply an operation, and then it's going to observe the results. So when you have an image and an action, and an image and another action and another image, and then at the end you can decide to stop. So this changes everything, because now the agent can see the effects of its actions. And most importantly, the order of the operations matter. So if you deblur and then you sharpen, is not the same as sharpen and then deblur. So the sequential setup lets the policy see the results of each operator before deciding the next one. So this is no longer prediction. Here we are doing planning. This is about understanding the multi-step decision making. The more technical term of this is credit assignment. So deblur at step 1 was the one that actually improved the downstream system. And a one-shot model would only get a single reward for the entire sequence. So it makes it harder to learn which operator contributed what. So the core difficulty here is not the enhancement, it's a credit assignment across a transformation chain. Which operation actually improved the system? Reinforcement learning gives us that mechanism to propagate that signal backward through decision. Imagine a slightly dark image right here. And so you can apply the gamma correction, and then you can say you are done. But now imagine an image that's actually more degraded. You have blur, you have noise, you have glare. You need multiple steps, and you don't know ahead of time how many steps you need. And that's why we introduce the stop action. So the agent decides when it applies the stop, it decides, okay, I've applied this, and now I don't need to apply it anymore. I'm going to apply a stop. So some crops, they only need one fix, and the others need multiple ones. Here it's a typo, so you can ignore this one. So it's exactly things like this that gives us a variable length processing. Sometimes it's short, and sometimes it's better to plan longer. And you're going to get feedback at each of those steps. And then you're going to have the ability to stop early or stop late. And so this is something a one-shot model can do, and that's another reason why we are using reinforcement learning here. Okay, so here is our setup. So we're going to start with camera. So you're going to get video feeds, for example. You perform detection, and here you would get crops, for example, of it can be anything. Crops of vehicles, crops of people walking. In this case, it makes sense to say it's crops of a vehicle. And here's the key part. The RL agent is going to sit between the detection and the downstream system. You're going to have an agent right here, and its only job is to fix the image that comes out right here so that the downstream model performs better. We don't care about aesthetics, we only care about the performance. So the RL agent is going to perform one enhancement step up to a certain number of enhancement steps, depending on the degradation. And once it's done, the enhanced image is going to go to the downstream systems. You can have multiple downstream systems. You can have one for OCR, you can have another one that's just like an encoder. Each downstream system can have a preference. So the OCR could prefer sharp edges. The embeddings here prefer consistency. So because you have different objectives per downstream system, now the agent needs to solve for a multi-objective optimization problem. And that's the entire loop. So part of the Markov decision process formulation, you can have a state. You also have the action space. You have the policy. You have the transition. For the action space that you see right here, it's going to select from a set of operations. So you can deblur, you can adjust the brightness, the contrast, you can sharpen, you can reduce the noise, and every one of these have a certain strength attached to it. And so every MDP has an action space. This is it. It chooses how strong to apply each of those operators, what to do and how to do it. And it repeats this up to a few steps until it decides to stop. Another part of the MDP is the state. What is the policy looking at in order to make a decision? And so the states can come in multiple forms. In this case, we're going to have a set of heterogeneous tokens. So it's a sequence of tokens, but it's not about the temporal sequence. It's not like a sentence. These are embeddings for different things we want to take a look at and see how they interact with each other. So one would be, how does my current image look like even after I've applied a certain number of enhancement operators? How did my image originally look like? I could have a vector that summarizes the kind of degradation that I think there is in there. It could be blurring, it could be noisy. We could also have metadata in terms of at what point did we see this crop, or what's the size of the crop, or where is the crop in the image. So these are things that can influence as well. And as we plan multi-step decisions, we always want to know what is the last thing we did, and that's going to affect our decision making. So this part is the state that the policy is going to see. So we have spoken about how the RL agent is going to apply operators to the images, not only to enhance their visual attributes, but to improve the performance of downstream systems. But this creates a new problem. It's called reward hacking. The agent might learn to exploit weaknesses. It will try to hack the reward. The real problem is designing a reward that is hard to gain. For example, here we can create a artifact detector that is going to pick up on unnatural image enhancements that we don't want. So we need safeguards. We want better visuals, but the image statistics need to be within a certain range. Another thing we can use is multiple signals. So from all of our downstream systems, not one. So if it gains one, the others are going to know that something's wrong. So as you improve one, you can add the penalty for something else. And so now the agent must balance competing objective. And so this is one of the strategies to make it hard for the agent to hack the reward, is that you want to balance competing objective. If you over optimize one, you're gonna hurt the other. And so that is a strategy that stabilizes the training. Okay, so let's talk about the algorithm. You can just say, okay, great, let's just throw PPO algorithm. But that doesn't work, because if you just throw PPO, it's gonna be a random policy, doesn't know much, and it's gonna apply all sorts of enhancement, and the rewards are gonna be very sparse. At the end, it's just gonna destroy the image. It's not gonna really learn anything. You can't let the agent start cold against real rewards. You have to prime it, because most of the actions are bad. There's only very few actions that are good. So the reward signal initially is very weak. So your learning is going to be super unstable. So instead, we train in stages. So we use 3 stages: behavior cloning, implicit Q learning, and then we use PPO. In behavior cloning, we're going to teach it basic good behaviors. The way we do that is that we generate good examples using brute force. We're going to take a certain input. We're going to apply a certain action. Let's say we're going to apply denoise. We're going to apply a certain strength. Let's say we're going to 40% denoise. And then we're going to get a better image. So we know this works. And so behavior cloning is going to take the action and the strength, and it's going to learn to map the state to the operator. However, behavior cloning does not reason about long-term consequences. So it's not optimized for multi-step sequences. That's where we're going to add the second stage, offline RL using implicit Q learning. So you need this stage in order to prime this stage. Now the IQL is going to learn which action lead to better long-term outcomes. This is where it does the multi-step reasoning. It's not going to try new things. It's just going to reevaluate what it has seen. And IQL underneath the hood is going to learn a value function that captures long-term reasoning. So behavior is going to say, here are good actions, copy them. IQL is going to say, here are the same actions, but now I know which ones are better than others for long-term rewards. I'm going to rank those that are the good ones, and I'm going to derank the mediocre ones. But remember, this is an offline algorithm, meaning it's limited to whatever is in an offline database or a replay buffer. So you can only do as good as this buffer. This is where PPO comes in, and this one, it's an online algorithm. So now the model can explore. It can try new combinations beyond what's in the data set. So just to recap, the behavior cloning, it copies from expert distribution. IQL, it learns a value under a fixed data distribution and re-ranks those trajectories based on long-term rewards. And PPO is going to adapt to the on-policy distribution induced by the model itself. So far, we've talked about what the agent does and how it learns. Now let's talk about how it actually makes decisions internally. And so here's the key challenge. It's that the input to the policy is not a single vector. It's a structured set of different pieces of information. So for every decision, and we spoke about this, the agent considers the current image, the original image, a vector that summarizes the kind of degradation in the image, some metadata, and the past history. You could also have features about the performance of downstream systems in there. And so this is the state the policy is considering. And these are the fundamental different types of information. And so the decision depends on how these signals interact with each other. So for example, sharpening might be useful, but only if the image is blurry, and only if we have already processed it, and sometimes depending on the camera. All of these combinations are encoded in the interactions between those tokens. So the question becomes, how do you combine all these signals effectively? And so instead of just concatenating everything into one vector, and that forces the model to compress everything too early, so you lose structure. So we don't want to compress everything into single hidden vector with a MLP. What we really want is a flexible interactions between all of these pieces of information, and this is what the transformer gives us. So through the attention, we let them talk to each other, and now the model can learn things like, this image is blurry, and the degradation says it's blurry, so deblur is useful. Or it can say, I already applied sharpening, don't sharpen again, so let me put a stop operator. Or it can say the downstream confidence is already high, so let me put a stop. So every token can look at every other token before making a decision, and that's the key idea. The decision is not based on one signal, it's based on the interaction of all of these signals. So we didn't use transformer because it's trendy, we use it because the problem requires reasoning across multiple interacting components. So now let's talk about something that's rarely explained. How do you know if the system is actually working? Because RL systems, they can fail in very subtle ways. They don't just crash. They silently learn the wrong thing. So you need to monitor the right signals. It obviously depends on the problem you're trying to solve. But the first thing we look at is the reward curve. Not just whether it goes up, but how it goes up. If it's a smooth upward trend, a bit like this, then it's good. If it does things like this, is high variance or it's unstable, it means something is wrong. So we want to look at the reward. Next, we look at the entropy. So the entropy measures how spread out the policy is over the actions. In our case, the actions are the enhancement operator. So if there's high entropy, meaning that if the distribution between the operator is uncertain, so it can be things like this. So here it's a bit uncertain about which operator is the right one, then the agent is unsure. If there's low entropy, that means it's more confident about some operators and then less about the others. And so that's low entropy. And so you want the entropy with time to also go a bit down. This way, it's a sign that the agent is more sure about the operations or the actions it can take. If the entropy collapses too quickly, maybe the policy is getting stuck in one operator and it's not learning diversity. If it's too high, then the policy never converges. We also want to look at the average steps per episode. So that's the number of enhancements. So depending on the degraded image, you can have from 1 up to a certain number of enhancements. And so if the agent keeps on using all of the steps, so let's say there's 4 steps, you can apply up to 4 enhancements. And so if every time you're applying 4 enhancements, something is wrong. It's probably not learning to be efficient. Maybe most are going to be 1 or 2, and some are going to be 4. So you want that to be shown here in the steps per episode. There's also the stop action frequency. So at some point you need to emit a stop. And the stop action just means I'm done applying this amount of enhancement for the image. And this is tied a bit to the steps per episode. So in healthy policy, it's going to learn to stop early whenever possible. So it's going to do as little enhancement that it needs. If it never stops, it's always over processing. If it always stops, then it's under processing. And you also want to look at the downstream task performance on a held out data set. That's very important because at the end of the day, that's what we really care about. And now that we've each signal individually, sometimes you want to see pattern between the signal, the interaction between the signals. So if the reward is increasing, but the downstream is decreasing, then the agent is overfitting on the reward function. Where if the entropies collapse early, then the policy has prematurely converged to a local optimum. So once all of these signals look healthy, we can finally trust what the agent is doing. So let's walk through a real example and see how all of this comes together. Let's start with a low light image, all right? For step 1 is that we're gonna apply exposure correction. And so the OCR is gonna improve slightly. Then we can also apply another step, we can apply denoise. And the signal becomes a bit better. Step 3, we decide, okay, I'm gonna emit a stop action because if I continue, it's gonna hurt the performance. And so this is the key. Every step is evaluated based on the impact on the final task, not based on how the image looks. So I hope this has been useful and thanks for watching.